and the screen share going. There we go. Looking at the website. So I've fielded a few questions from folks who are currently working on homework 3. Does anybody have questions that they'd like to be answered at this time? Because I'm happy to do so. Is it hard? uh, I don't think so, but I am not a good judge of that. I would say that it isn't asking you to do anything that I haven't demonstrated in example 3. So from that perspective, there's a finite amount of difficulty. There's nothing that you have to come up with from asking the Google or off the top of someone else's head besides mine. So those of you who started, would you like to weigh in? Is this hard? You can be honest.
I so I did the first computational and the second I'm just finished section 1. It took me a while to get going, and I agree. I don't think it's too hard, but I did find myself going back to my notes, going back to the lecture. I even once popped open a video and tried to find where I thought you talked about something. So I am referencing what we've talked about.
So that's exactly what I wanted to happen. Holy
Oh,
shit.
okay.
Yeah, this is the idea is to give you practice because these are the kinds of things that you would be doing in real life, but it's also to try and to get you to review the material from a different perspective, right? Because you can sit there and listen and think, yeah, I'm following this. This seems okay. And then you get to the program and you're like, now what? And that getting through that process is what the homework was designed to do. So, yay.
One thing I forgot to do, please don't forget this. I forgot to go and grab that starter code. So I was trying to piece it together from my homework 2 starting code. And once I realized that's what I should have done, and that would have saved me probably 45 minutes this morning. So,
Okay. Yeah, it is the same data, but I have a starter syntax for every homework. That way you don't have to do that part yourself yet. But all right. Other comments, questions? All right. Then do you want to start talking about some new stuff today? Well, you came, right? So, I mean, you want to do something. So we have a new lecture and example to dive into, and homework is up for that, as well as the next formative assessment, which is due in 2 weeks. So those are available if you want to get started on them. Let me get to PowerPoint. Here we are. And I'm going to try and move this thing out of the way. Hide floating meeting controls. Control Alt Shift H. So presumably that's how I get them back. I have a hard time getting them back. All right. So yes, saving is important. Yes, that brings up a very good point, especially inside the virtual desktop. Sometimes if you lose connections or it hangs, it won't let you save. I have been in that situation when using the virtual desktop, and if you can't somehow get back to save your file, you should be able to copy it. So you can select all and copy the text and put it into a different place. That way you don't lose your work. So if your session does get disconnected, that is an emergency route to make sure you don't lose your stuff. All right, so we have on as our next topic, continuation of general linear models, but with more stuff in them. So moving past just the idea of redoing Pearson correlation, moving on to look at as a set, the idea here is fitting the effect of a predictor that's going to take more than one slope to capture its full relationship. That's the general theme here. And so I have specific instances of when you would want to do that, or when you would need to do that rather. And the first one that we're going to talk about corresponds to the missing bivariate relationship that I said you needed a model for. So the idea of a bivariate relationship between a quantitative outcome and a nominal variable. We're going to do that in a model. So that is first up. And that, by the way, is otherwise known as analysis of variance. So the shortcut for that is ANOVA. So now here's another thing you can add to your technical skills section that you know how to do. Analysis of variance is actually a terrible name for what I'm about to show you because it has almost nothing to do with variance and has everything to do with mean differences across levels of a nominal variable. So it should be analysis of means, like that would be the term that would make more sense. But as you've learned, the name that makes the most sense is not the one we use. We want to make sure that it's confusing as possible because then that's job security. Because if you crack the code and you learn the lingo, then somebody will hire you so that they don't have to. Alrighty, away we go then. Ding ding, one more person joining us here. There we go. All right, there. So, reviewing, what have we covered so far with respect to these models? Um, the idea behind general linear models is to create a custom predicted outcome variable for each person in the sample. So the term general linear model, the linear part, just to remind you, means that the model takes this particular form, constant times variable plus constant times variable. And the word general specifically means that the residuals of the model, so the discrepancy between what the model says the outcome is and what the data say, those residuals are supposed to be normal. Otherwise, the standard errors are going to be some kind of incorrect. And we've seen two variants of this so far. One is the empty model. So this is the first thing you get to practice in homework 3, for instance, where the term empty means no predictors. The empty model isn't something that you would necessarily estimate in real life, but I'm using it here for pedagogical purposes to get you used to the idea of what is the model trying to do. What it's trying to do is to predict what the outcome variable is going to be for any person in your sample. And so the worst model you could have, the naive jumping off point, is if you guessed the mean for every single person's score. That's the worst you could do. And so if you fit this empty model, the fixed intercept here, our friend beta 0, takes on the sample mean, and E is the difference between the y that's observed and the sample mean. And we calculate the E's variance across individuals. That term is called residual variance because it's the variance of these E residuals. And in the empty model, that represents all of the variability that there is to be had in the outcome. So that's all of the information that we have that we're going to try to predict with information about the person that goes in the model on the predictor side. Okay, is this all sounding familiar? Okay, questions or clarifications so far? All right. Then the next thing we did is add a single predictor. So in terms of my notation, predictors are X's, outcomes are Y's. Let's review vocabulary. Give me the synonyms that you know for predictor. What might someone else call a predictor if you're reading a manuscript, for instance? IV, yep, independent variable. That word tends to be used for predictors that are manipulated or assigned, not things that are measured, but one could use that. How about for, oh, criterion, that's on the Y side. Criterion is a synonym for outcome. How about a predictor that someone else cares about who's not you? Starts with a C. Control variable, I'll take that, or covariate, yeah. Mathematically, they're all X's. Whether or not you care about the results or whether or not the order in which you might put them into the model, that has to do with your research questions and how to best address them. But X is just with a predictor. Good. So yeah, on the Y side, a synonym for outcome would be dependent variable or DV or criterion. So any of those would work to describe outcome variable. So in my model here, I've got one predictor now, and I've got one outcome. I'm going to have one outcome for the rest of the semester. If you want to learn how to predict multiple outcomes at the same time, what should you do?
Go to your next class.
Yes, come back. Yes, if you come back in the spring, you can learn how to analyze longitudinal data as a specific type of what is known as multivariate analysis, or when you're trying to predict multiple outcomes at the same time as is needed, say, to measure change or growth. So yes, and you are all welcome to join that class. It will meet at 2 o'clock on Tuesdays and Thursdays, but it will be the same format. I will be hiding in my basement for the foreseeable future. Um, So univariate analysis predicting one y. So far, we're predicting one x. This is what's known as simple linear regression, by the way, if it's a quantitative x. If x is binary, this is known as a independent groups t-test or two-sample t-test. And we have our vocabulary. So once we have a predictor in the model, then the intercept is the expected outcome when that predictor is 0. And that's why we're going to be centering predictors if 0 isn't already a meaningful value to make sure the intercept is interpretable. The slope, beta 1 in this case, is the change in y for a 1 unit change in x. And E is the residual. It's always going to be the discrepancy between what the model says and what the data say with respect to the outcome. So it's the data minus prediction, and where prediction is this y hat thingy right here. So that holds what the model says the outcome should be for any one person. And after we put in x, what do we hope to see happen to our residual variance, this sigma squared E? What should it do if x is a useful predictor? Should it go up or should it go down? This is a go down, yeah. So the variance of the e's across persons should shrink because the idea is that by putting x in there, there's less discrepancy between the model and the data. Okay, I think that was all I was going to say about that. Oh, what is the worst that x could be? Like if x did not matter at all, what would beta 1 be? Yeah, this is one you can do hand gestures to. 0. Yeah. So if beta 1 worked out to be 0, then x is not associated to y. And so we wouldn't expect the residual variance to change much. It might go down a little bit, but the question is whether or not it went down significantly. More question. So if x matters, we know that because the significance test for beta 1 tells us so. X matters if the slope for beta 1 is significantly different than 0. If that is the case, then we know automatically that the lowering of the residual variance was significant too. It's a one-to-one combination. So the slope is what tells us about the change in the variance. All right, so more specifically, when looking at the slopes, we want to pay attention to the estimate itself. So the sign tells us the direction of the relationship. If the slope is positive, that means as x goes up, y goes up. If the slope is negative, as x goes up, y goes down. We also want to pay attention to the standard error because that tells us the expected inconsistency of our slope across samples. And if we take the estimate and divide by the standard error, that gets us to our t-test statistic, or the t-value, as I will say forever and ever. And that requires denominator degrees of freedom to be able to reference our t to the right distribution, and that will be provided for you on the output. Denominator degrees of freedom is based on sample size minus the number of fixed effects it took to fit your model. So up to this point, if we just have a fixed intercept and a fixed slope, that's 2 fixed effects. So k would be 2. And then last but not least, this beta 1 slope is in the metric of whatever x is and whatever y is. So the slope is the change in y for a unit change in x. To know what that means, we have to know what a unit is. So just knowing the slope doesn't give us a sense of how big the relationship is because the size of that coefficient is going to be dictated by units. So we need to also supplement the analysis with some measure of effect size. And so in general linear models, one way to do so, of many, but one way to do so is to ask for what's known as a standardized slope. And the formula to go back and forth is right here. The standardized slope is whatever the unstandardized slope was multiplied by the standard deviation of the x predictor and then divided by the standard deviation of the y predictor. And you can get software to give this to you. This is what proc-reg is used for in SAS, or the beta option in STATA on the regress statement. Either one of those will give this to you. And if you are in a situation where there's only one predictor in the model, then that standardized slope is exactly the same thing as the Pearson correlation. Once you leave that situation, though, once there's more than one predictor in the model, that will not be true anymore. The standardized slope will not be the same as the Pearson correlation because it will mean something different. And so we'll talk about other ways of indexing effect size and how that has to change when we have more than one predictor in the model. Okay, I think that's, yes, almost it. Okay, let me pause. No, go back, please. Go back. Not that far back. There we go. Okay, this is where I wanted to pause and say, do you have questions? Or is there any of that you want to hear again or hear differently? No? You're good?
Actually, I would like to hear it again, please.
Which part?
Um,
Or from where, I should say.
from the I got the estimate and then the standard error and how the slope just gives us this the is it the direction, but it doesn't give us the effect size.
Okay. So yes, the slope, the direction matters. A positive slope means that as x goes up, y goes up. And a negative slope means that as x goes up, y goes down. So direction matters. But the number itself, like if I told you that the slope of a variable was 4, you'd have no idea what that means. I'd have to tell you what the variables are, right? If this is in pounds or years or dollars or like what is a unit, right? Because it's 4 just means that's how y is supposed to go up for every
So,
unit change in x.
Mhm.
Jake
And
added some questions he wants me to answer,
okay,
and these are it. Okay. Hold on.
okay, Tasha, are you talking to me or somebody else?
Do you and Chad own the LLC together?
I think someone else.
Okay.
Okay. Administrator control. Problem solved. Okay. So 4, that's where I was, right?
Right. Yeah.
So is 4 a lot?
We don't know.
Exactly, because it depends on what the units are. And so if I went from, say, pounds to kilograms, right, the slope would have to change because of what 1 means, like for a 1 unit change. So we need to strip the units off of the slope. We need to put it into a metric that is unitless, and that's our R correlation metric.
Mhm.
Because then if I told you, oh, I have an R of 0.4, you know how big that is. And so the conversion formula here takes away the units
Okay.
to put the standardized slope into a correlation metric that we immediately know what it means. So the direction will stay constant, but it just rescales it. So it would be if you z-scored your variables. So if you converted both your predictor and your outcome into a z metric where the means are 0 and their variances are 1, then the unstandardized slope would be the standardized slope.
Sorry, I'm sorry.
I love the honesty. She's like, yeah, no idea what the hell you just said. That's okay. And that's actually going to be one of the things I illustrate at some point in the handouts. But yeah, so another way of thinking about this is if you went to the trouble to strip the units away from your variables to begin with,
Okay.
then the result that you would get back out of your model is a standardized slope.
Okay. Let me just sit on it for a little bit and then
Okay.
I'll come back to you.
Okay. But the main thing is that like just reporting that the slope is 4 and that 4 is significantly different than 0 is not enough.
Yeah, I got that part. Yeah.
Okay, if you got that, then that's what I want you to get.
Okay.
That's what I want you to get.
The other
Because
one, yeah. Okay. I'll
fair
I'll
enough.
sit on it. Maybe it'll become more clear. Thank you.
That's fine. Yeah, the more times you go through it, the clearer hopefully they will get. The practice makes perfect, just like everything else. Or as my husband would say, perfect practice makes perfect, which is apparently a sports reference of some kind. A coach of the 49ers or something. Yeah, anyway.
Wait, I have one more question. Can you say some again? Can you repeat the part of the denominator with the degrees of freedom? Like, what were the 2 degrees of freedom again? I'm sorry.
So in the model, let me go back here. So we're talking about a model that has one slope in it for one predictor.
Mm-hmm.
Degrees of freedom is n minus k is the formula. N is sample size. K is the number of fixed effects, the number of betas in your model. The number of quantities that you had to estimate from your data in order to create a predicted outcome for each person. And so you can think of degrees of freedom for the denominator as like a point system, because I could predict each person's outcome perfectly if I just said, okay, well, you get a slope, you get a slope. I'll be like Oprah with the cars. You get a slope, you get a slope. I gave you each your own slope. That would predict the outcome perfectly. I could spend all my degrees of freedom, but I don't want to do that. I want to try to predict as well as I can, but still have as many points left over as I possibly can. So the idea of degrees of freedom is sort of a penalty function for, okay, yeah, you did a good job predicting your outcome, but how complicated did your model have to be to pull that off? And so we keep track of that in estimating how good the model is, because we want as good a prediction as possible, spending as few degrees of freedom to do it. The idea behind that is parsimony. That's a buzzword that you will hear.
Got it. Thank you.
Sure. Okay. Any other questions or parts that you want to hear again out of that? Okay. Then, new stuff. So at the end of last time, and the last section on homework 3, you get a chance to practice having a binary predictor variable. And so if we have a binary predictor, we only need to estimate 2 fixed effects to tell us 3 pieces of information. We have an intercept, which is going to be the outcome mean for the group that's coded 0. The slope is the mean difference of the one group relative to the 0 group. And I'm saying that very carefully because 0 is the anchor point, the reference. So if I have a positive slope, that means as x goes up, y goes up, but that's hard to think about in the context of a group. A positive slope means that the one group is higher in their mean than the 0 group. A negative slope means that the one group is lower than the 0 group. But than the 0 group is the baseline because they're your intercept. They are the you are here sign of your model. And so the third thing that you might want to know is, okay, well, what is the mean in the one group? And that's a linear combination. So if we add the intercept to the slope gets multiplied by a 1 because that's what the value of group is, then that linear combination gives us the mean for the other group. So even though there's 2 means, I only need 1 slope because I have the intercept. So it's 2 fixed effects necessary to recapture my 2 means, and the means will be captured perfectly. So what we're going to do today is extend that logic to deal with predictors that are grouping variables that have more than 2 groups. So we'll start with 3, and in homework 4, you get a chance to practice with 4 groups. Hooray! Yes! I'm going for challenging, but in a good way. So that's my goal. So if I have 3 groups. And I'm using the word group and category interchangeably. I'm slipping into ANOVA language because they talk about groups and group mean differences in ANOVA language. Farhan, you're in design of experiments right now, right? Okay, this is going to sound very familiar if any of you are in that class with him. So we're talking about one variable that has 3 groups. And we're treating this as if it's a nominal variable, meaning that the groups have no ordering and we're just going to compare each of them to each other. At the end of this very long lecture, we'll talk about the idea of how to test whether or not an ordinal variable could pass as interval. That's a separate issue. But if I have 3 groups, then I need 1 intercept and 2 slopes. And that will perfectly recreate my 3 means. If I have 4 groups, I need 1 intercept and 3 slopes. If I had 5 groups, how many slopes do I need? 4, yeah. And then that will perfectly recreate all the means. And if the model recreates all the means, then the model also recreates all the mean differences. So one of the things that I want to teach you as part of this is how to ask for the mean differences that are implied by the model but not directly given by the model, because the slopes are only going to give you some of them. The others are going to be linear combinations. And more generally, here is a formula you can use to figure out how many possible pairwise mean differences you have across your groups. This is a specific form of the n choose k type of formula where you're choosing 2. So if you need to figure this out, here's how you can do so. And by the way, what we're talking about today is ANOVA. So first things first, we're going to have to take our categorical predictor and transform it into a series of binary variables. Because my categorical predictor, even if it has values of 1, 2, 3, they're not real numbers. I have to convert it to a series of binary variables as my first step. So here's the coding scheme that I'm going to need shown in the table, and then the code down below is what it takes to actually make your software do this. So let's say that in continuing the GSS example, we're still predicting annual salary, income, as our outcome variable. And today we're doing it from a self-report. What level of class would you say you are? Are you low class, middle class, or upper class? And I expect that one's designation as to their class should be related to their income level. Not a very interesting research question, but it works for our purposes. So here are the sample sizes for each group. So here's another new piece of notation for you. Capital N is always used for the overall sample size. Lowercase n is what is used for sample size within a particular group. So you will see it written like this in method sections. For instance, when people name the groups, they will give lowercase n as to how many was in that group in particular. And I give the sample sizes here as a point of reference. The upper class, only 20 people out of 734 labeled themselves as upper class. So right off the bat, what do I know about power with respect to this upper class relative to the others? Yes, this is another gesture question. Yeah, I'll take a thumbs down or a little eensy beensy. Yes. Yeah, so I need people to be able to find differences that are significant. So with only 20 people, I'm kind of facing an uphill battle. So just keep that in mind in the back of your head that when you're looking at grouping variables, you need to have enough people in each group to be able to find differences. So here's my 3 groups. So what I'm going to need to do is compute 2 new variables for the data set. One of the new variables I'm naming L versus M because its role in the model is going to be to distinguish the low group from the middle group. The other variable I am naming as L versus U because its job is going to be distinguishing the low group from the upper group. So these are names that I came up with. This is how I name variables. It's always the reference is the first versus the alternative is the second. And I have a 0-1 coding scheme in place that does this designation. So this coding scheme more generally is known as dummy coding. it makes it so that one of your groups is going to be the model reference as the intercept, and it is always the group that's coded 0. So if we think about why would that be, well, the definition of the intercept. The model intercept is always expected outcome when your predictors are 0. So by creating these new predictor variables in which the low group is coded 0 in both, I am setting them up as the reference. So the low group is my "you are here" sign, the 0 group, so to speak. In the first column here, low versus L versus M, I am giving the middle group a 1 because I want them to be the comparison. But if we look at the values here, 0 is not all the way split yet. If I want this to be low versus M, or L versus M, that isn't done yet with this column because the upper group has a 0 as well. So I need one more variable that then splits apart those zeros. And that's the role of the next one, is that it will distinguish low versus upper. So these two variables work together. If you were to put either of them in the model all by themselves, you would not get what you wanted out of it because they work as a pair. So when they're both together, the first predictor is going to give you the difference of how the middle group differs from low. The second predictor is going to give you the difference of how the upper group differs from low because of this coding scheme. So one of the things that you will have to decide is how to set up your variables so that they map onto effects that you care about. There are lots and lots of different ways to do it, and I'm going to show you a couple other variations, but this will be the first one because this is by far the most common approach, this idea of dummy coding. You make one of the groups the 0, and then you contrast that 0 group with each of the others in turn, and this coding scheme accomplishes that. Okay, how are we doing? Yeah, this is the intersection of stats and computing, is trying to get the computer to do your bidding. There was a student last fall, her name was Kelly, and she was hilarious, and she referred to this as sorcery. What sorcery is this that I can put zeros and ones in and get this information out? Yes, it is sorcery. It's very cool, I promise. So here's how I can tell the computer to do this sorcery for me. First in SAS. So note that any data transformations have to happen after this data set combination, but before the run. So think of those as like a sandwich, right? Like data set is one piece of bread, run is the other piece of bread, and your transformations have to happen in the middle. STATA doesn't have that. So the first thing that I'm going to do is create 2 new empty columns. So L versus M is the name of the new column. I'm setting equal to a dot, which means missing. Same thing for L versus U. Note that each of these ends in a semicolon. The analogous STATA code is down here, the gen. Each of these equal to a dot, no semicolons in STATA. Then conditional recode. So if the original variable that we have here, this grouping variable, is called work class. So that's what I'm starting with in the data set, and its values are 1, 2, or 3. So that corresponds to low, middle, or upper. Then do. I have a series of things I want it to do. That's why I have the do and the end. So I've shown you earlier versions of this where it was just then. I'm adding the do because I want to do more than one thing if work class is 1. So it's a set of conditional statements. And so then I'm going to create 0 values for the first column and 0 values for the second column. If group is 2, then I turn on the first column, set it equal to 1, the second column stays off. And if it's 3, then I turn on the second column. And the same thing happens down here in STATA, just with the backwards order. So the if part goes at the end, and then replace is the coding that happens in here in SAS. Okay, so let you stare at this for just a minute. Does this make sense? Ish? Are there aspects of it that you want to hear more about? No. Okay, yeah. By the way, we're creating a design matrix. So you may hear about that in other classes. That's what we're doing here. So here's what's going to happen then in terms of what the model tells us. So I've got 3 groups. That means that I have 3 means that I want to recreate here, 1 for each group. It also means that I have 3 mean differences because the low group can differ from middle, middle can differ from upper, and low can differ from upper. So what goes into my model then are 2 of the differences. That's what the slopes are going to tell me. Because of the way that I coded these variables, beta 1 is going to be how far off the middle group is from the low group. Beta 2 is going to be how far off the upper group is from the low group. So I have 3 fixed effects. That's going to perfectly recreate my 3 means, and this is how it happens. So if I just go through and fill in for each of my groups here, the 0 and 1 values that I gave my binary predictors, it works out that the mean for group low is given just by the intercept. That's what the intercept means. The mean for the middle group is the intercept plus the difference. So the intercept for low plus the difference of going from low to medium gets you up to middle, excuse me. And likewise for you, we start with the mean for the low group and we pick up the difference to get from low to upper, which is beta 2. So then the 3 mean differences, 2 of them are given directly. So because low is the reference group, any mean difference relative to low has to be in the model. So the slopes give us the comparisons with low. What's not in the model directly are comparisons involving the non-reference groups. So we know how different low and middle are. We know how different low and upper are. What we don't know is how different middle and upper are. And that one, though, is a linear combination. So if we take the mean for upper and subtract the mean for middle, we end up with the difference of the slopes becoming the missing mean difference. So you'll get a chance to ask the software to find these things for you. This is our friend estimate statements in SAS or lincom statements in STATA to be able to get linear combinations of things. All right. So we'll look at that in just a second here. So what we're trying to do is at the top. The code to make it happen is at the bottom. So the model directly gives us the mean for the low group, and it directly gives us the mean differences of low versus middle and low versus upper. So that's what will come out on the fixed effects, those 3 things. The other 3 things that I would want to know are the means for the not reference groups, middle and upper, as well as their mean difference. And so I've written out 6 statements down here that give us all the pieces of information, all 3 means and all 3 mean differences in one place. That way I don't have to do the work later on of trying to figure out what these would be from 2 different places. So low mean on the estimate statement here is filling in this equation. I need 1 intercept to make the low mean. I don't need either slope because the low group was coded 0 for both of those. So it works out that just the intercept is the low mean. The middle mean starts with the intercept. I need 1 of those. I need one of the beta 1 slopes because for the middle group, they are coded 1 on that variable. They are coded 0 on the other variable, and so I don't need any of those. And likewise, for the upper group, I need one of the intercepts. I don't need any of the first slope. I do need one of the second slope, and that gives us the third line down here. So, do I have to write the terms that have the zeros in them? What do you think? If they're zeroed out, do I need to write them? I don't need to. Why am I doing it? Because I love typing? No. Pedagogy. I'm trying to show you how the statements, the estimate statements, map onto the equations. So I'm leaving in the zeros as placeholders. But if you don't like typing as much, you don't have to write the terms and have the zeros. But if you're filling in these statements for multiple groups, it can be helpful to include them just to remind yourself what all terms would contribute to the prediction. Okay, so are we okay-ish with the means? Not yet? Thank you for your honesty. What would help make it okay? Wine. Ba-doom-tsh. That is correct. Unfortunately, it's a little early for happy hour. That being said, if wine makes it better on your end, knock yourselves out. I've got the opposite right here. I've got the uppers instead of the downers. Yeah, this stuff takes practice to see the logic of it. It does get easier with practice, but it isn't easy to start with. I can give you that. This next three statements give the mean differences. So the first two are redundant with the slopes. They're just going to spit the slopes back. And the third is the one that's not given directly by the model. It's how you get the mean difference between the groups that are not the reference groups. It works out to be, if you figure out what the model says the mean should be for each group, so beta 0 plus beta 2 is how we get the mean for the upper group. Beta 0 plus beta 1 is how we get the mean for the middle group. Then if we subtract the mean for the middle group, the beta zeros cancel, and we're left with just beta 2 minus beta 1 as the linear combination that gives us the missing mean difference. And that subtraction is shown with the negative 1 in the last line. So the beta 1 has a negative sign in front of it up here. That's the negative that goes in front of that variable. And then the 1 is because beta 2 is positive. No negative in front of that. Okay. STATA code looks very similar, except it has asterisks for explicit multiplication of the constants and plus signs to show it maps much more directly onto the equation. So the plus signs are implied otherwise. One catch in STATA. Have you seen this before? I can't remember if I've talked about this before. This C dot thing. Okay, this is new. Predictor variables in STATA are either C dot or I dot. I am deliberately not teaching you I dot yet, but C dot just means that it's being treated as a quantitative predictor. For reasons that are unclear to me, if you want to use the predictor in linear combination statements like this, you have to have C dot in front of it. Otherwise, it will yell at you. So that's why you will see these in front of all of the predictors that are being treated as quantitative variables, which these binary predictors are at this point. Okay. So this is all a lot of abstract stuff. Would it help to put some numbers in here? Numbers always help, right? Yes. Numbers and wine, to be fair. That would be a good combination of the two. So here's a slide that has a bunch of numbers and stuff on it. I'm going to show you how to make SAS and STATA spit these numbers out for you. So that's where these came from. So if we start with an empty model for income, the estimate for beta 0 is 17.3. That's the mean for the sample. So if I don't know anything else about a person in this sample, my best guess for their income is whatever the sample mean is. It works out that the average person is predicted to make $17,000 and $17,300. The variance of the E residuals at this point, the residual variance as it's called, is 190. So that is all the variation in income that there is to be had that my model is going to try and explain. So here's my model. I am now asking if income differs across 3 different types of people. People who rated themselves as lower class, people who rated themselves as middle class, or people who rated themselves as upper class. So I want to know, broadly construed, if the income levels that are observed for the sample are consistent with people's ratings. I would expect that people who rated themselves upper class make more money than people who rated themselves as middle class, and they make more money than people who rated themselves as lower class. So I need to figure out what the means are for each of these groups, what the mean differences are, and whether those mean differences are significantly different than 0. So if class rating matters, then I should see these slopes be something other than 0. So here's my solution. By the way, the term solution for the fixed effects means the answers. So solution is a fancier way of saying the answers, the result. So my intercept, beta 0. Definition of beta 0, always. Expected y when your predictors are 0. Okay, so what does that mean in this context? When is beta 0? It corresponds to the low group. So both of these variables are 0 that we've created to go into the model when the low group is what we're talking about. So the estimate for beta 0 is 13.65. That means people who rated themselves as being lower class have an average income of about $13,000. Okay. So note in this equation, even though the original variable is work class, that's not in here. Likewise, when I go back to the code, that original variable that has the 1, 2s, and 3s, that's not in here. So we're working with the 2 new dummy-coded predictors that I created to designate binary group status. And I need 2 of them because I've got 3 groups. Okay. Are you with me so far? Okay, so I have a standard error of 13.65 that came with it. And if I take the estimate and divide by the standard error, that gives me a t-value that results in a p-value that's very small. Now, question for you. Do I care about this p-value for the intercept? Deborah says no. No, I don't. Why don't I care about that? Any guesses? What does this p-value right here tell me? Can you see my big giant pink thing here? Okay, what does that tell me? Because normally it would be like, hey, it's significant. Woohoo, I get to talk about it. But what does the significance test refer to if I'm talking about the intercept? Yes, mean of low is different than 0. That's what this is telling me. So my reference group makes some money. That's what I've just learned. So only in a situation in which 0 as a reference point for your outcome variable has some sort of meaning would you care if the intercept is different than that. So don't be fooled. You're going to see that the intercept is often very different than 0. That just means that the outcome variable's mean for that type of person is not 0. In contrast, the slopes. I care about the p-values for the slopes. The p-values for the slopes tell me how unexpected it would be to find a slope that big if the true slope in the population were 0. So the estimate for the first slope for beta 1 is 8.85. That's a mean difference. More specifically, this slope estimate of 8.85 tells me that relative to the lower class group as my reference, people who labeled themselves as middle class make an average of $8.8 thousand more. So the slope is the difference between the groups. If I take that estimate, divide by that standard error, that gives me my t-value, and the p-value that goes with that t is significant if we use any cutoff pretty much. That means that if the true slope were 0, it is very unlikely to get a slope of 8. So we would say that this slope is significantly positive, meaning that people who have the 1 in this variable, the middle group, have a higher outcome mean than people who have the 0, which is the low group. Okay, how are we doing? Not yet. Okay, I'm asking more tentatively now. It's like, I know. So what I know so far, the low group makes $13.6 thousand on average. The middle group makes significantly more by 8.8. What's the middle group make? Yeah, 21-ish or 22. Yeah, 13-ish plus 8-ish. Yeah, somewhere in there. So if we look down here, here's the math. Here's what the model says. The middle group is whatever the low group was, which is the 13 for the intercept, plus the difference to get to the middle group. So if we add those two together, the other slope is not relevant because we're not talking about the upper group right now. That does work out to be 22.5. And that mean is also different than 0, but who cares? So what I've learned so far from the model parameters is what the mean is for the low group. That's the 13, the intercept. I've learned what the mean difference is going from low to middle. That's beta 1, the slope for the binary variable that I created to separate the low and middle groups. And if I put the intercept and I add the slope to it, because the slope gets multiplied by 1, that's the value for the group, that works out to give me a mean of 22. So that much we did last time at the end of lecture 3, and you guys get to do in homework 3. That much you got. So that much is, technically speaking, review. Okay, are you ready to add on then? Or do you want to hear any of that part again? Hear parts again or add on? Okay, votes for add on. If you don't vote, then you don't get to participate. All right. Okay, we got votes for add on. Question, is the p-value of 0.482 significant? What do you think? The last one down here. No, what does P need to be in order to use the label significant? Yeah, more hand signals. 05 or 01. Yeah, take your pick. It's whatever alpha level you decide to set. If you want to be conservative, make it 01. If you want to be traditional, make it 05. But we'll get to that one in just a minute in terms of how we get there. But yeah, that's the one thing on this page that's not significant. Slope number 2. Slope number 2 is distinguishing the upper group from the low group. So relative to the low group, whose mean is 13 given by the intercept, the upper group's mean is higher by about 11. So people who rated themselves as upper class make $11,000 more on average than people who rated themselves as lower class. That estimate divided by its standard error gives us a t statistic, and the p-value that goes with that t means that the slope is significant. So it's a significantly positive slope. People who rated themselves as upper class make significantly more money on average than people who rated themselves as lower class. And you may be saying to yourself, duh, but people are reporting their class accurately? I don't know what you'd make of that, but it's a toy example for now. So how much money do upper class people make then? 13-ish plus 11-ish, right? That gets us to 24-ish. That's the second line down here, 24.63 if I work through the math. And that is also significantly different than 0, but it's a mean and so we don't care. So now I've got all three means. The intercept directly tells me the mean for the low group because I've coded the two predictors such that low is the 0. The slopes carry the mean difference for each of the groups coded 1 when both of these predictors are in the model at the same time. And so now I can get the last comparison. If I look at this slope that differentiates low versus middle, that's 8, and I look at this slope that differentiates low versus upper, that's 11, the difference between those slopes creates middle versus upper. The difference between those slopes is 2, with the standard error of 3, which creates a t-value under 1 and a p-value that's 0.48. So in other words, if we had a true difference between middle and upper that was 0, we would find a difference this large like 48% of the time, well within expected sampling fluctuation. And that's because even though there's a mean difference of $2,000, which might sound like not 0, the standard error for that is 3. Like, it has no idea what the mean difference is. It could be 2, it could be -2, it could be anything. So to put that into context, a standard error of a slope tells us how far off a sample slope is from the population slope on average. So if the average wiggle is 3, then us finding a 2 means we're well within expected territory. Okay, how we doing? Starting to get there. The example helped. Good. I like examples. They do help. All right. So the residual variance then. Should it have went up after adding in my predictor or down? Down, yes. And it did. It went from 190 down to 171. Is that good? Is it good enough? I don't know yet. Because there's no longer a one-to-one correspondence between the change in the residual variance, it going down, and the predictor that made it go down. I've got two predictors here. And those two predictors create another predictor, essentially, the remaining difference between the non-reference groups. So those two predictors create three differences. So the residual variance could have gone down because of one of those three differences, two of the three out of the three, I don't know yet. So we have to find a way to test both of those slopes at the same time to be able to make a decision as to whether or not this decrease in the residual variance is noteworthy, is unexpected, is significant. And that's going to require a new letter, F. And you may be thinking, yeah, F that. But no, really, we are going to F that. That's coming. All right, that's what's next. But before we spend a little more time on this, what do you think would happen if I screwed up my analysis and I made these two variables, but I forgot to put in the second one? So I just put in L versus M and I didn't put the other one in, and I left it coded like this. So if we just focus in on this column right here, what would that analysis then tell me? The uppers would be added to the lowers. Yeah. The zero group would become the average of low and upper. A weighted average because they're very different sample sizes. But yeah, they'd get smushed together. So I would have the zero group would be the intercept, which would give me an average of those two together. And that average then would be compared to the middle group's average as the slope. So the interpretation of what is being compared to what only holds if they're both in the model at the same time. Let me ask you another question. Why do I need to do this? What if I took the variable that's low, middle, upper? It's coded 1, 2, 3 in my data set. What if I put that in as a predictor instead? Could I do that? It's a free country. I can do whatever I want. Would SAS or STATA estimate it for me if I did that? Yeah, it will. Yeah, it will. SAS and STATA do whatever you tell it to. They do not judge you or weigh in on whether what you're doing is a reasonable thing. But let's think about this. Here, let me escape for 1 second. Come on. I'm going to put the labels on here to help with the working memory load of what we're talking about. This right here. So working class is a variable in my data set. Come on, you can do it. There we go. Where this group is coded 1. This group is coded 2. Come on, you can do it. And this group is coded 3. Okay. What would happen if I put that variable in as my X, as my predictor? what would I get? Well, what would my intercept mean? Let's start there. The intercept would give me the expected outcome when I'm at group 0. I don't have a group 0. I've got 1, 2, 3. It'll still give me a number though, even though that number doesn't mean anything. It wouldn't be meaningful. So what if I thought, well, Lisa told me I need to center everything, so let's just fix this and like that. That's a little better. So now my intercept would be the low group, but I would get one slope. One slope. A slope is always the change in y for a 1 unit change in x. So it would be a number. Let's say the slope based on these is going to be, let's go with 9. Let's say the slope worked out to be 9. That would say for every unit increase in class, income goes up by $9,000. Now, is that meaningful? What is a unit increase in class? Well, one of the units is going from low to middle. The next unit is going from middle to upper. So I'm saying then that moving from 0 to 1 gets me $9,000, and moving from 1 to 2 gets me $9,000. If I fit one slope, that's the same thing as saying that there is a constant difference between these groups. Now, is that consistent with the data? Not at all. There's a jump of 8 to get from low to medium, but a jump of only 2 to go from medium to upper class. So if I fit a single slope, that's the same thing as saying that the groups are equidistant with respect to their outcomes. And now I fit a slope through these because low, middle, upper arguably are ordinal variables, and you see things like that all the time. But what if this was, say, Paw Patrol, PJ Masks, and Peppa Pig? Is income higher in families whose children watch PJ Masks versus Paw Patrol versus Peppa Pig? Now, will SAS and STATA let me put a line through that? Sure they will. But does it make sense to go from one to the other as X goes up, transitioning from TV show to TV show? No. So the things to watch out for when you have a categorical variable like this is to make sure that it is represented as a series of binary variables. Otherwise, it don't make no sense. Even if the software will let you. Later in the unit, I will teach you how to actually test whether or not there's equidistant differences between the groups for ordinal variables in particular, whether or not it's okay to put a slope through something like this. All right. Questions? Any that you want to hear again as review before we sign off for the day?